All right, well, good morning. My name is Steve Marr. I'm with Risk Management Professionals, and hopefully everything's coming through on your end. Welcome to our ongoing outreach program dealing with PSM, Process Safety Management, and Risk Management Program topics. But before we get into that, please make note of the phone number on your screen, 877-532-0806. That's the number to call if you're having any technical problems on your end. And by the way, for those of you in the audience who did call this morning and also emailed us that our website is down, it just shows you nothing's 100% reliable. We haven't experienced that before, but there's always a first time. If there's any problems with this broadcast, though, please do call in. Anybody who didn't get the slides, they should have been emailed out to you about 45 minutes ago. Anyhow, welcome. Before we get too far along, the mouse. All right, very good. Before we get too far along, let me tell you about the interface we're using and the sort of things you can do on your end. We're using a GoToWebinar interface. You have the ability to resize the screen with my image. You also can resize the screen with the slides. The slides should be synchronized with the package that got emailed to you. Also, during the course of the presentation, if you do have questions, they can be put on your chat interface to our producer, Karine Black. And also, we've got assistance from other folks in the office, including Sarah Willman, who's graciously watching this as it's being broadcast to make sure there's no hiccups and that you guys can see everything okay. So before we go any further, also a quick recap on what Risk Management Professionals is about. We are PSM RMP consultants. We do specialize in PHAs. Typically, heavy industry calls us for that primarily, because HAZOP and LOPA are known specialties for us. There's also some new requirements in California for safeguard protection analysis. That's SPA requirements. Those dovetail very, very closely with HAZOP and LOPA activities. For smaller facilities, small and mid-sized facilities, people do call us in to completely develop their programs. We do provide full scope services for PSM and RMP, and also for a lot of the new requirements associated with inherently safer technologies, hierarchy of hazard control analysis, and safer technology and alternatives analysis, STAA. So a lot of these things are very important to your programs on site, and basically that's what we do. Because we get involved in all these things, wide range of facilities from onshore facilities to offshore facilities, we do try to share our technical expertise as a part of our outreach program, and that's what this webinar is all about. So let me go ahead and introduce the topic to you that we're going to discuss today. Using HAZOP and LOPA to create an effective mechanical integrity program. The key takeaways that I'd like you to walk away from this webinar today are how PHA, basically HAZOP and LOPA, and mechanical integrity programs are interrelated with respect to their implementation, and also secondly, how to use PHAs to make your mechanical integrity programs more effective. Keep those in mind. That's what I want you to walk away with this today. Also, I'd like to introduce our speakers, me, Steve Marr, and Max Opedal. A little bit on me. I've been around the block a few times. I've got a couple of degrees, a couple of professional engineering certifications, and I've had the privilege of being involved with some really cool activities over the years, not only for industry level activities like the CCPS, but also some very cool projects. I think it's a factor, it's a reflection of the fact that people call me in if they've got nearly impossible problems to solve, and then if I'm not successful, they've got some nice contractor to blame that they can make go away pretty easily. So anyway, I've been involved in some really cool projects, and I've got a lot of publications that try to reflect some of the things that I've learned over the years and encapsulate them for everybody's benefit. The one thing we didn't do, and this occurred to me last night, is I wrote a paper with David Childs on this for the 2017 Global Congress on Process Safety, this being mechanical integrity programs and using HAZOP and LOPA. There's no reason why you guys shouldn't have that paper. We'll make sure everybody who attends this webinar gets a copy emailed to them. And I'll ask Karine to make sure that happens later today. Thank you, Karine. Okay, a little bit about Max. Well, enough about me. Let's talk about somebody important. Max Opedal will be taking care of the more important parts of the presentation. that focus on some of his experiences with developing effective mechanical integrity programs. Max is a chemical engineer, and he's really looking forward to sharing some of his experiences with you. Before we go any further, a couple of key topics. Um, Actually, before I even discuss the topics, let me go ahead and warn folks who are experienced practitioners in PSM and RMP. A lot of these concepts aren't going to be new to you, but our experience when we go out to plant sites is that people struggle with the basics. When you get large teams of people together, some developing mechanical integrity programs, some doing other PSM and RMP elements, a lot of times they have trouble fitting the pieces of the puzzle together. We always find that the programs aren't as effective as they could be if people can see the big picture and make good use of all those resources that are available to them. That's the main thing. That's one of the key things we want to get across today. To do that, we want to define mechanical integrity, make sure we're all synchronized, talk about some high-profile events involving mechanical integrity failures that pinpoint why this is so important. Also, why are we doing process hazard analysis, and how can we use LOPA to enhance our process hazard analysis experience? Pulling it all together with mechanical integrity, other methodologies that complement what you're doing as part of your PSM RMP program, a little bit about statistics that you should keep in mind when applying some of these numerical methods to mechanical integrity. And one of the reasons I gave you or suggested the chat win interface for Korean Black is at the end of this, we're going to do a QA session. If you have questions, you're welcome to use that interface. Also, we have the ability, even though everybody's on mute right now, so we don't have 50 or 100 people having their office activities all being broadcast. At the end of it, if you'd like to chime in or participate in a conversation or dialogue, we can also arrange that too by unmuting you on the GoToWebinar interface. So let's go ahead and get started first by making sure we're on the same page and defining mechanical integrity. To make sure that we synchronize our understanding of mechanical integrity, sometimes it's important to understand how we got here. What you see on the screen are three distinct timelines, one associated with regulatory developments for onshore facilities, primarily in the United States. The second arrow, offshore facilities, primarily in U.S. waters. And the third, facilities that are outside the United States where there were accidents that led to the development of safety cases. In all different areas and also different time frames, unfortunately, because as humans, we all tend to be a little bit reactive, both as individuals and also in groups. So it's really not until something bad happens, like some of these horrible tragedies that you probably recognize in the photographs, Opal, Deepwater Horizon, Piper Alpha, that people step back, look at the lessons learned, and start applying them. The interesting thing is that regardless of the location, type of facility, whether it's onshore or offshore, all these led to the development of similar safety management systems, which is the overarching term for PSM, RMP, SEMS for those of you who are in the offshore business, that describes how to pull these elements together. So what do we have now, and what are those key elements? There are kind of two major categories. One is associated with understanding your system and identifying potential hazards. Process safety information and PHA fall into that category. The other side of that is how do you manage those hazards? Mechanical operating procedures, also training, and also mechanical integrity. Mechanical integrity is the one we're going to focus on today, and that's part of the management part of safety management systems. So let's talk a little bit about why it's so important, and we'll talk about some high-profile events that are associated with mechanical integrity failures. Many of you have looked through your history books about the Flicksboro event in 1974, recognize it as a mechanical integrity issue. Basically, if somebody put in a temporary bypass and they hadn't really looked at all the parameters that were needed to make sure that temporary bypass functioned properly and didn't result in a loss of containment. Major mechanical integrity issue, and also a little bit an issue associated with identifying potential hazards. Many of you may have known some of the folks who were affected by the Texas City accident in 2005 at the refinery. Basically, a number of things occurred that shouldn't have with respect to starting up a unit, but a key part of that was really not really understanding the hazards, really identifying what could go wrong if key equipment failed, and then key equipment, such as in this case, high level liquid alarms, um, not working properly, allowed the accident to reach a point where you can get a loss of containment, release of large quantities of hydrocarbons, then of course a major event following that. The key takeaway from that is that you've got to understand the importance of various equipment failures. You really have to identify the hazards and look at that as part of an overall scenario so you can characterize how important a safeguard is and what kind of reliability it needs. So that's where we're going with respect to how PHA and mechanical integrity can work together. So let's talk about why do a PHA. We already talked about how mechanical integrity failures can have very significant consequences. And yes, PHA is required by regulation, and a lot of people have suffered through HAZOP studies or LOPA studies to try to identify hazards. But it's really that understanding of the hazard and what can go wrong that leads you to the framework where you can understand how important equipment reliability is and distinguish between equipment that needs a little extra attention or higher reliability and equipment that may not need quite as much. We'll talk more about that in a few minutes. All right, so there's a large spectrum of PHA tools. A lot of you recognize some of the simpler methods, such as what-if checklist, and also hazard techniques, and a lot of the more complicated techniques, such as bow tie, event tree analysis, and fault tree analysis. In the middle of that is HAZOP, and a little bit to the right of that is LOPA. Those tend to be the workhorses, regardless of that they do take some different forms when you apply them, and of course everybody applies them a little differently as an individual, at different plant sites, and within a certain company. They're all applied a little bit uniquely, but they all have a certain framework associated with them. That framework allows you to characterize the undesired events in terms of how likely they are and how bad the consequences are, or that severity. And you really need that understanding to really bring it back to the importance of equipment reliability. So let's talk about LOPA and a little bit about that. Most of you, I think, are probably familiar with LOPA, or layer protection analysis. That's probably why you're tuning in. But a lot of you may not have thought, other than, gee, do I really have to do this, to what you can do with it and how you can actually use that productively to actually save a lot of money at the plant and make things safer. And we'll talk more about that in a few minutes. So to understand LOPA, let's remind ourselves of the risk framework for most of the different PHA techniques, other than the very simple ones such as what-if checklist. Most of them are pivot on an understanding of the hazard, the severity of the event, the consequences of the event, the severity associated with the consequences, and the likelihood of the event. And the key objective isn't, of course, you have to satisfy regulatory requirements. Somebody may be making you do it, but the key thing is supporting decision making. You're trying to put things in a platform so that you can understand the hazard and support decision making. Part of that decision making is, what do you do with your preventive maintenance or mechanical integrity program? And so these different PHA techniques, and again, we're focusing on HAZOP and LOPA, most of them have in common trying to characterize the severity and likelihood so that you can make effective decisions and swing that right back to your mechanical integrity program. So to help us understand a little bit about how some of this reliability information can feed back into your mechanical integrity programs and how you can use LOPA for it, it's important to understand where we're at right now. Over the past couple of decades, there have been some dramatic improvements in the application of electronics, understanding of equipment reliabilities to make the safety systems more and more reliable. Many of you are familiar with safety integrity levels, SIL 1, SIL 2, SIL 3. It's becoming easier to have higher pedigree, more reliable equipment. Well, what happens then? If you got higher pedigree, more reliable equipment, it allows us to design systems that can operate at higher temperatures, higher pressures, or drill deeper and further to push the limits even further in terms of our engineering technologies. And of course, what does that mean? That means we have to go back to the drawing board and reassess our safety features and make sure that if we need to raise the bar with respect to their reliability, we do so. So there's a big cycle that's been going on over the past few decades with respect to analysis, going back to understanding equipment reliability, allowing our systems to be designed even closer to with reduced safety margins or at higher pressures and temperatures. And then, of course, which requires more analysis and maybe even more improvements in equipment reliability. So if you go to any given refinery or major processing facility, you're going to see a wide range of different equipment out there, from very simple analog devices that just sit there and do their job, and they've been doing their job for decades, so nobody even wants to mess with them. Sometimes people don't even know how they work, to very complex voting logic, feedback devices, self-assessment devices that will tell you if something's wrong, that feed into large electronic control systems. And you see a wide range of all these different types of features at different plant sites. Well, the real challenge with PHA and HAZOP and folding this into the mechanical integrity program is, what do you do with that wide range of systems? You really need tools that can help you assess the reliability for all these different types of systems, very different architectures, different pedigrees, a lot of times different amounts of design information even available to those. And how do you pull all those together for effective decision making and fold it into your mechanical integrity program? Well, it turns out LOPA is really an ideal tool for that. LOPA is really taking PHA when you're looking at the causes, safeguards, and the consequences, and putting some numbers on them, usually order of magnitude numbers, so you can take a look at what really constitutes risk or the importance of a scenario, which is really its likelihood times its severity. The way LOPA does that is basically it's a large multiplication of all the different probabilities that go into enabling conditions, all the different probabilities of failure and demand of your safety systems, all the different probabilities associated with conditional modifiers, and pulling all those together to get a clearer picture of what your scenario frequency is. And of course, embedded in that scenario frequency is the failure rate of the initiating events and also the failure probabilities of key safeguards, which of course folds right back in your mechanical integrity program. So the LOPA helps define what you think the system, define what the risks are based on your knowledge of equipment reliability. And in the same way, the mirror image of that is that it tells you what equipment reliability you need to maintain to make sure that you've got the risk levels that you've reviewed, analyzed, and have considered acceptable and meet the risk acceptance thresholds of your company. So it's a big cycle. The HAZOP and LOPA identifies a scenario which feeds into the needed equipment reliability that you need to maintain. Then your mechanical integrity program maintains it and also provides feedback. Maybe something's not as reliable. Maybe something's even more reliable than you thought it would be, and that can feed right back into your assessment of risk. So these things are heavily interrelated, and it's important to keep that in mind as you're developing programs, maintaining programs, and you make decisions on where to focus your energies in terms of maintenance. And we'll talk more about that in a little bit. But right now, I told you Max was going to be telling you about some key things based on his experience and some other mechanical integrity issues. So I want to turn the podium over to him and let him go over some things. And I'll come back in a little bit for a little bit of summary and also to kind of help with the QA session too.
So give me a second to get everything set up from this. The mic is working. Cool. Okay. Let me just go back. So pulling it all together. There are 7 parts that all together create an MI program. The parts are requirements, program management, procedures, training, inspection, testing, maintenance, repair, documentation, and feedback. Requirements consists of creating a system of inspection intervals for the system, usually the best industry practice is according to API, IAR, and manufacturing manuals and alike. The program must be managed by someone, for example, a maintenance manager for larger systems, or maybe just one person does management and actual maintenance for smaller systems. The procedures for the maintenance are known for the individual process. Procedures should be documented so maintenance can review when needed, and the level of detail in the procedures depends on the process and complexity. Training is important so new people are given a good time frame to practice and learn how to perform the maintenance on the system. This can be done with written procedures or just shadowing. The next part of the steps for the MI program is the actual inspection, repair, maintenance, or testing. The outcome of the test or repair should be documented, and the comments should be used to change the testing intervals. This is encompassed by the documentation and feedback parts. The requirements help make the program, which is then managed by the maintenance staff. This is an overview of how they all work together. Maintenance staff, and then the procedures are created for the program, which maintenance staff are then trained on. Once training is complete, the inspection can be performed and then the results documented for the maintenance supervisor to create new requirements. This is a living, ever-changing system depending on the results of the tests. This allows people to track and learn from past mistakes. If a pump is breaking down every 10 months, but only has a 1-year inspection interval, then it might be wise to start inspecting the pump every 6 months. This will allow for a more reliable pump and scheduled downtime rather than unexpected downtime. If a pump breaks down, the process can be completely stopped without warning, which can be devastating for a facility. A strong MI is possible when the 7 steps communicate with each other. Also, if one of the parts are deficient, then the whole program will suffer since they are all intertwined. Without the correct training, then the maintenance staff might not perform the correct task, and the documentation and feedback will suffer. And the requirements will not be changed without good feedback, and then the program will then not be managed correctly. Okay, this slide shows a figure for the different types of implementation of the MI program. When I say MI program, I am meaning mechanical integrity program. There are 2 columns on the left which show the potential effectiveness of different types of maintenance programs. Usually post-it notes are not more effective for keeping a preventative maintenance program than a simple scheduling software which reminds you. For computerized maintenance management systems known as CMMS, there are 2 columns which show how to better achieve MI implementation with a CMMS. An industry-focused CMMS might be better for your facility than a broad-focused CMMS. Not every facility needs the latest and greatest CMMS specific for their industry to implement the MI system well. For some facilities, especially a simpler one, post-it notes might work great. The MI program is based on the performance, and if everything is being maintained in a preventative way, then there is no problem. RMP and PSM are performance-based standards, as we all should know. The more complex the MI implementation is, the harder it is for somebody to understand it. A more complex CMMS will require training for all maintenance staff and continuous involvement. This might not be the best way to improve performance of the MI program. So, complementary methodologies. The easiest way to create an effective MI system is to look through standards like API RP 581 and others involving your field, and using those standards to determine intervals and potential safe procedures. It is better than guessing when a pump should be serviced or a tank be inspected. Once the standards have been used, they will always be a resource, but feedback from the actual inspections might be better for determining what the best inspection interval is. This is true of industries which do not have many process safety standards. Using the information from the maintenance inspections and the information from the type of service and how the service is performed, damage mechanism reviews can be performed. Okay, so on that slide, there is the enhanced contemporary best practices for maintenance of piping and also identifying possible areas of corrosion. Then there are prioritized DMRs, which damage mechanism review stands for, DMR stands for damage mechanism review, approaches which focus on what could potentially cause damage to different pieces of equipment in different processes. The integrated process hazard analysis, or IPHA, is a combination of a PHA and a DMR. This allows the information gathered in the PHA to use the information of the damage mechanism review more readily, and allows the DMR to use the information from the PHA more readily. An MI-centered risk-based assessment is a extremely rigorous and detailed assessment where all the possible damage mechanisms are quantified and reviewed. Also, for everyone's note, we are in California, and DMRs are now going to be required with the promulgation of 5189.1 and CalART Program 4, which will promulgate on October 1st. The regulations state that no less than 50% of the initial DMR shall be completed within 3 years of the effective date of this article, and the remainder within 5 years of the effective date of this article. This needs to be revalidated every 5 years, similar to a PHA. I just want to remind everyone, these new regulations only apply to California refineries. The risk-based inspection is going to look at the general and local metal loss due to corrosion, surface-connected cracking, subsurface cracking, microfissuring, microvoid formation, and metallurgic changes. This is expanded in API 571 for information on how to perform this damage mechanism review type review. RMP wrote a paper 5 years ago discussing the possibility of creating an integrated PHA. If anyone didn't know, PHA stands for Process Hazard Analysis. It's a key concept of our core component of the RMP PSM program. So a DMR are done at the same time and integrated together with the PHA. So those are integrated together, and it allows us to do one large review at once rather than trying to do them separately, and then also they can work together. If you want, RMP also did a webinar 2 years ago about DMR integration into the PHA. If you want more information on any of these subjects, please feel free to email me or info@rmpcorp.com, and we'll send you the information in the previous webinar handout. So select statistics to optimize the MI program. Okay, so there are two types of repairable components we talk about in this webinar, which are monitored repairable components and unmonitored repairable components. For equipment with monitored repairable components, there are two states which are shown in the y-axis of the top graph, which are the operating state and the failed state. The x-axis shows time. So as the equipment is operating over time, the equipment will fail, and it will take some time to notice that the failure has taken place and to fix the piece of equipment. Failed states are not desirable because they can slow production and decrease efficiency. The second graph uses the average over time of the operating state and the failed state to find percentages of the time that the piece of equipment is available. A piece of equipment is available 100% of the time at startup, but the availability goes down once the piece of equipment has failed. This allows one to make decisions concerning each individual component and how often to do inspections if the availability is known. To define the terms on this side. So A is availability, Q is unavailability, MTTF is the mean time to failure, MTTR is the mean time to repair, and lambda is the failure rate. So MTTF is how long the piece of equipment takes to fail. So it's active time. It might sound a little confusing since the one with the term with failure in it is actually its active time. If it's active for 29 days, then if a piece of equipment is active for 29 days, then breaks, the MTTF is 29 days. And then if it takes 1 day to notice the failure and fix it, it means the MTTR is 1 day. These are directly correlated to the failed state graph on the previous slide. These are the total times over the course of a chosen time period, which is based on what you want or the data that is available. Remember, the MTTR includes not only the time to repair, but also the time to notice that a failure has occurred. This is extremely important for developing SIL ratings. A SIL rating is given to an alarm based on its likelihood to fail. The higher the SIL rating, the less likely it will fail because the alarm is tested, protected, and given an independent power source. LOPA is very similar because they both assign likelihoods through numbers, like 10 to the negative 2 chance a PRV will fail. Lambda multiplied by the MTTR, which is shown on the slide, will also give the unavailability, since the failure state is much smaller than the operating state. So 10 to the negative 6, which is 1 e to the negative 6 per hour, times 10 will give you 10 to the negative 5. Okay, this is the equation for unmonitored repairable components. Monitored repairable components are looked at much more frequently than unmonitored equipment. So a PSV is not monitored, but only tested or replaced after a set period of time to avoid failure. A pressure gauge will allow one to monitor a pump at all times by an operator. The component unavailability is the mean time of unavailability divided by the mean time of interest. The mean time of interest, or tau, is the time between each test of replacement, or like replacement of PRV every 5 years in some cases. These equations are meant to show the correlation between unavailability, failure rates, and time. The equations shown show the mean time of unavailability is lambda times tau squared over 2. The unavailability is lambda times tau over 2. A monitored piece of equipment will take more credit if it is monitored. So in order to counterbalance that unmonitored pieces of equipment tend to have more rigorous repairs, like full replacements, to gain extra credit in LOPA. Okay, so nothing is obviously perfect, and issues can materialize at any time for a myriad of reasons. There will be variance in the inspections and testing intervals and methods, because inspections will not always take place the same day every 3 months, and not every maintenance personnel does the exact same procedure. The first time period a piece of equipment is used is one of the most likely periods for the piece of equipment to fail. Some pieces of equipment are not built to shut down, which can make maintenance difficult during an outage. Also, some pieces of equipment are more critical to the system and might need to be repaired right away for startup. A system which normally uses 2 pumps might be okay to use 1 pump, while the other more important repairs are being completed, especially if the pumps are not known to fail. Sometimes the observations given as feedback are not correct and can lead to problems. By understanding your equipment, you can optimize your process and fix equipment in the order of importance. Maintenance managers tend to learn the system and do this naturally, but having documentation and proof can improve consistency. So we're going to bring up Steve for a quick summary of everything that we talked about in this webinar. He will be up in a second. Do you want to? Okay.
I'm off mute. Am I coming through okay? All right. Let's see these. Okay, good. We're in the summary. So there we go. Maybe I will make that a little bit bigger. There we go. All right. So what have we been talking about? Yes, there's a lot of really cool stuff you can do statistically. Max gave you some of the basics. You can go beyond that to apply Bayesian statistics to take your observed failures at the plant site and infuse them into the kind of failure rates that you use when you're applying LOPA and other things. There's all sorts of wonderful things that you can do. But most of the improvements that we've seen have been at a fairly basic level. Really, the mechanical people are managing the mechanical integrity program, working with the people who do the rest of the safety management system, interfacing that with the PHA, using the results of your field observations. If something's failing all the time, fold that back to into your LOPA. Understand what the implication of those failures are. Or if it's not failing, if it's very robust, if it's tested properly, and it's not failing over long periods of time, great. Go ahead and feed that good information back into your LOPA activities, your PHAs, so that you can actually use those results to make better decisions on, do you need redundant equipment? Do you need improved equipment? Or is what you've got just fine? So basically, you're using this interface between mechanical integrity and HAZOP and LOPA to really enhance the effectiveness of your mechanical integrity program, which in turn enhances your safety margin and the safety that you're providing to your plant personnel. You want to make sure that you use these results to ensure that high priority equipment gets the attention needed. If something's breaking down too often and it's got a high failure rate, go ahead and focus your energies there. If something is incredibly important for 99% of your HAZOP scenarios, maybe that's where you should be focusing your mechanical integrity program and your attention rather than on other things. The people who are part of your MI program, they're very busy. Your resources are probably stretched. Knowing where to apply those resources is super critical. Okay, so you can use the HAZOP and LOPA to optimize inspection, testing, and preventive maintenance frequencies. You can use the observational information from your maintenance department to feed back into HAZOP and LOPA. Another key thing is really identifying what's not important. What sort of things can a very busy maintenance department kind of put aside and not worry about too much? One of the things that we do a lot, I mentioned what risk management professionals does. We get involved in a lot of HAZOP and LOPA for heavy industries. A lot of that is involved with capital projects when people are putting new designs together. I've written papers on this before, but you can use HAZOP and LOPA to really accelerate the progress of the project. Well, in a lot of cases too, you can identify where the design may be over applied, or maybe you're putting too many safety systems in. The instrumentation folks on your design team may be having a lot of fun putting in safety instrumented systems in a lot of places, but if you don't know why you're putting them in there with that perspective of HAZOP and LOPA, then really you're just making a maintenance nightmare for people to have to do the extra inspections and testing associated with safety instrumented systems. So using HAZOP and LOPA during the design process to identify where you don't need to apply high pedigree safety systems is just as important as knowing where to apply the high pedigree systems. So again, it's all about decision making, using the HAZOP and LOPA to optimize your design, optimize your mechanical integrity program, and making sure that your resources are put into an area that really optimizes plant safety. So again, I hope that this was beneficial to you and that you got a lot of this webinar. Before we proceed to the question and answer session, while you're thinking of the questions and typing them out for Corrine to read to Max and me, I just wanted to let you know that we do have several other webinars that are coming up as part of our outreach program. We've got one coming up on the importance of RMP and PSM prevention program elements for mitigating hazardous releases. We've got one on RAGAGAP, and also I mentioned earlier of some of the changes that are coming up with respect to PSM and RMP. Federal level's been stalled a little bit. I think most of you are following the RMP program updates with the EPA. In California, just about a week and a half ago, the Office of Administrative Law did finally authorize the promulgation on October 1st of CalARP Program 4 and PSM 5189.1 for refineries in California. Those things do require several new features. DMR, I'll come back to this. Damage mechanism reviews, I'll come back to DMR in just a second. Safeguard protection analysis, SPA, and hierarchy of hazard control analysis are key elements that are going to require a lot of additional work. There are some other elements to help organize your management system and your organization itself. We'll be talking more about those in a webinar that's currently scheduled for September 12th. That'll be of acute interest to refineries and other heavy industry, especially in California. Also, before I forget to mention it, for DMR, Max mentioned that there's additional information available. We did write a paper at the 2015 Global Congress on Process Safety. If anybody's listening to this webinar and would like a copy, please send us an email, let us know, we'll ship a copy out to you. Mention the RAGAGAP. We're also a sponsor and exhibitor at the upcoming RITA National Conference. We got upcoming webinars on common cause assessments in an application for HAZOP studies, as well as solid and powder dispersion modeling. So I got a lot of really good things coming up. Again, our outreach program is tuned to taking things that we feel industry needs and providing some basics so that you can move forward with your programs. If there are topics that you feel, other topics that you feel are worthwhile to address, things that may be troubling you, maybe others can benefit too, let us know. We've got quite a library on our website, and if it's a new topic, and we can point you to that, and if it's a new topic, it might be worth us putting something together for everybody's benefit. Okay, so I'm going to invite Max back up, and we're going to go ahead and field some questions if you have any. And let's see, where am I? There I am. Oh no, I'm in the blue shirt. You need to come over this way. Okay.
All right, we have a couple questions for you guys. The first is, how can I convince management that there is value to LOPA application?
You want to get started?
You can get us started.
Okay, good. Yeah, okay, good question. The question was basically, how can I convince management that there's value in applying LOPA? That's a good question. Anytime there's a new technique, management gets especially nervous. They're trying to balance the books. Management's trying to keep everybody employed, actually. So you want to focus your resources and energies on things that matter. Well, if you just do LOPA for the sake of LOPA, it is valueless. It's not going to help you one bit. But if you do apply LOPA to get more out of your PHA, to provide a framework for optimizing your mechanical integrity program, for optimizing your design, it can be used to save a lot of money while making your plant safer. These are words that management wants to hear. So if you want to go ahead, characterize it like that, and that is absolutely correct, those are terms that they'll understand a lot better than even telling them what LOPA stands for.
Okay, next question is, how are the LOPA values for initiating cause likelihood determined? Can I change mine based on facility experience?
You want to get started?
Sure.
Okay. Uh, there are quite a few text guidance books out there for not only the failure frequency of initiating events, but also the failure probabilities for key safeguards such as relief valves and active components. Center for Chemical Process Safety has one. ARADA has one. There's a variety of books out there that provide detailed failure rate data. As part of LOPA application, there are basic order of magnitude approximations of failure rates that are easy to apply. That's why LOPA exists. It's a simplified quantitative risk assessment tool, and by applying that, it gets you started. It's basically another level of screening beyond HAZOP studies. Now, there are fancy techniques out there. If you have, well, not so fancy techniques. If you actually have empirical data at the plant site, there's no reason why not to apply that. That's probably the most applicable to your equipment anyhow. But if you have, there's something called Bayesian statistics where you can take generic failure frequencies and morph them based on the statistical weighting of your data with whatever plant data you have, even if it is minimal. So all these things are meant to enhance the LOPA experience, and basically so you can get more out of your layer of protection analysis. Max, anything else?
I would just like to say that different people will use different like probability of failures. Even though a PRV could be considered 10 to the -2 at one site, it could be 10 to the -4 at the other. We've noticed that the proportions for the target like frequency though have been the same. If you're using a 10 to the -4 PRV, we found that the target frequency for the LOPA was high or lower technically than the one if you were using 10 to the -2. Also, a lot of different facilities will look different. Their LOPAs will look different. They might use 10 to the -2, or they might just say over 100. Sometimes it just all looks different, but usually it all means the same thing, and it's fairly similar across the field.
So I think Max brought out a good point in that these generic failure frequencies are based on a typical service and an environment. If your environment and service is more corrosive, it's more demanding on the equipment, you'll want to adjust your equipment failure frequencies accordingly. And on the flip side, if it's a more benign application, you may either use a more conservative number that comes out of a generic textbook, or you can and say it's conservative and you have a lot of safety margin, or you may adjust it accordingly. And actually, an understanding of that is as important as the actual numbers. If your layer protection analysis shows that you're on the fence with respect to needing more safety features or being okay as is, and then you have the realization that the equipment is in benign service and you've had good experience with it, it may go ahead and push you over the fence to say what I've got is just fine. Next, Corinne.
Okay, this
I
is
think
the
I'm gonna have
last
to get taller
question.
here.
Last question is, how do I know if the CMMS I am using is right for me?
Sorry.
So usually CMMSs are all different. You know, as we said in the webinar, you can use one that's very broad or one that's very specific to your industry. The biggest reason to look for a new CMMS is if you're not happy with the current one, or the preventative maintenance, the maintenance is not getting performed on time and accurately. So if you don't think you're getting the maintenance out of it, there's no reason to use a CMMS if it's not being used correctly or no one's using it. And that would be a good time to look for a new one. Also, it's a performance-based standard. So if the CMMS is performing and you're happy with it, you should keep it. But if you're not happy with it, you should really look for another one, because there are quite a few CMMSs on the market.
Okay, no, that's good closure. It is performance based. Some facilities do better with something that's web based and simple that requires minimal training. Other folks have a very involved program, and there are a lot of packages out there that can provide a lot of depth to your assessment. Green, anything else? All right, well, let me thank everybody for tuning in. And if you do have any follow-up questions, let us know. We will send out the email with the paper from this year's GCPS. And good day to you.